Okay, so let me go to the final exam. Problem 1, you have to know what a derivative is and how to use the definition of a derivative to compute one. But that's a problem we had dozens of times in the beginning of the semester, definition of the derivative, and to use the definition to compute from a very basic function, the first derivative. Then you have L'Hopital's rule. Then you have implicit differentiation in computing the equation of a tangent line. You have to find the first derivative and the critical points. You have to discuss a function, even, odd, limits, vertical asymptotes, intercepts, increasing, decreasing, maxima and minima, concave up, concave down, and all that. One function you have to discuss. Then there is Newton's method, how to solve an equation, and the problem about the left endpoint, the right endpoint in the trapezoidal rule. Then there is a word problem, an optimization problem. Some of the problems is, you can choose one of them, so you don't have to do both. You can choose, there's always A or B, so you have a choice what you do. Then there comes problem 8. That's what I want to concentrate on today. So it is an integration problem, 45 points out of 200 points, 8 integrals which you have to evaluate. Then you have another 35 points, a problem where you have a region. You have to compute the area and the volumes if you rotate the region about the axis. And you have to set up everything with vertical and horizontal slices. And that's again a problem I want to cover today. And then you have a problem about averages, how to compute averages, and the problem about the fundamental theorem of calculus, part 1. And that will be the final exam. I think each and every problem is taken from one of the tests, very close to the tests. That's what you should prepare for. When you prepare for this, you should do reasonably well. Any questions about the final exam? Okay, then if there are no questions, then let me proceed now doing some problems, some integrals that one of you asked for, and then do a volume problem by rotating certain regions around certain axes. So for this, let me share my screen. Okay, so can you see my screen? Do I hear yes? What did I lose you all? I'm sorry, I cannot hear anything, so I'm not sure. Good. Okay, now I see that I have some chat responses. Good. Okay, so let me start with the integrals. So the first one, the integral of the sine of x divided by cosine squared of x, or cosine to the 3 of x, or the square root of x, or anything like that. Now, how would you compute this? Now there are many ways you can go wrong. So let me write one of the ways. That would be what I call algebra. You try to rewrite it. You could write it as the sine of x over 1 minus the sine squared of x dx. That's perfectly okay. You would get partial credit, but now you did not simplify the integral. You complicated it. You made it more complicated. So at the beginning you try, and at a certain point you should think, okay, what else can I do? And the standard way, one of the standard ways to do integrals is by U substitution. And as a U substitution, you always pick as U a function that is inside and or a function where you also see the derivative of this function, where you see U prime floating around. And again, that is a rule that works in many cases, not in all cases. In this case, it would work. So if you take U equal to the cosine of x, then U prime is minus the sine of x. And yes, I see the sine and I see the cosine. So by doing this U substitution, you can transform the integral into sine x dx is minus du, and 1 over cosine squared is 1 over u squared du. Or if you want, it's minus the antiderivative of u to the minus 2 du, and by the power rule, this is then u to the minus 1. Now you stop, check if it's true. If you take the derivative of u to the minus 1, the minus 1 comes down. So it's minus u to the minus 2, that is correct. And now you go back, so it's minus 1 over cosine x plus c. And if you want to be nerdy, then you write this as minus the secant of x plus a constant. So that was a typical problem, how to do a U substitution. This case, I think, a fairly straightforward one. Okay, let's go to the next problem. Which is very, very similar in nature. Again, you have a sine and a cosine. Let me again do the more complicated way. So you try first some algebra to simplify it. Now you know the antiderivative of the cosine. This is easy. So this part is already taken care of because the antiderivative of cosine is sine. So you really have to look at cosine x, sine x. And then if you have a good cheat sheet, there is a formula on your cheat sheet that this is 1/2 sine 2x plus the cosine of x dx. And now you can integrate the antiderivative of the sine is minus the cosine of 2x. But if I take the derivative of this, I get 2 times the sine of 2x. So I really need here a minus 1/4. And then the antiderivative of the cosine is the sine, and I have a constant. So that would be one way doing it, which I think is the complicated way. Another way doing it is by a basic U substitution again. You take U equal to sine x plus 1. So that's in a parenthesis, that's an inside. And I see the derivative because then du dx is cosine of x. And if I plug this in, then star becomes the antiderivative. Cosine of x dx is du, and I have u du, which is 1/2 u squared plus 1. And 1/2 u squared gives you then the same as 1/2 sine x plus 1 squared plus, why do I have 1/2 u squared plus 1? Where does the plus 1? I have no idea. It's plus c, plus a constant. So we have here the result. So the integral is equal to this. And before we showed that the integral is equal to this. And also by a miracle then, by the trig identities, it has to be that minus 1/2 sine x plus 1 squared is the same as minus 1/4 sine 2x plus sine x. And then somewhere you have a constant, yeah? And the constants might be different. So the constant here might be different than the constant here. Both results are correct, depending what method you choose. Okay, now next problem. The integral from 1 to a plus 1 squared of x plus the square root of x over x squared dx. Again, the first thing, this is always what I do in my mind, I try what happens if I do algebra. Now the first two examples, if you do algebra, it really doesn't help you. There the u substitution is better. In this case, the u substitution, no matter what you do, would be painful. And I will show you this in a minute. In this case, the easy way is to do the algebra just by dividing it through. You get in the integral from 1 to a plus 1 squared. X divided by x squared is 1 over x. And the square root of x divided by x squared is x to the 1/2 over x squared is x to the minus 3/2 dx. So by doing the algebra first, in this case you have an integral you can handle. So the antiderivative of 1 over x is the logarithm of x. In the antiderivative of x to the minus 3/2, you add 1 to the exponent, you get x to the minus 1/2, and then you multiply with the reciprocal. So it is the same then as, and you have to evaluate this between 1 and a plus 1 squared. So you get, if you plug it in, the logarithm of a plus 1 squared minus 2 times the square root of a plus 1 squared. So this happens when you plug in the upper bound, minus, if you plug in the lower bound, you get the logarithm of 1 minus 2. And now if you simplify it, the 2 comes down, 2 times the logarithm of a plus 1. The square root of a plus 1 squared is 2 times the absolute value of a plus 1. The logarithm 1 is 0, and the minus minus gives a plus 2. So that will be your final result. And that is by doing algebra. Now u substitution, you could take u equal to x squared, u equal to the square root of x, u equal to x to the 1/2. There are many things you could do, but whatever you do, the integral will not get easier, it will become more complicated. So I don't even go there, I will not cover this. So that is a clear case where algebra first is helpful. Now the next integral is again a trigonometric integral with secant squared and tangent. So if you know your tables of derivatives, you should know that the derivative of the tangent is secant squared. So now you have a pairing, u equal to tangent, u prime equal to secant squared. You see u and u prime floating around, so that will be the u substitution that we use. If you do algebra, there's a formula that tangent squared plus 1 is secant squared. So you could write this as tangent squared plus 1 e to the 100 tangent x. But if you do this now, you are trapped. The integral is correct, you transformed it, but you transformed it into a more complicated integral. In this case, again, the u substitution will be u equal to tangent x. Then du dx is secant squared. And if you plug this in, now you get what? If x is 0, tangent of 0 is 0, then u is 0. If x is pi over 4, the tangent of pi over 4 is 1. So you go from, u goes from 0 to 1, x goes from 0 to pi over 4, then tangent x goes from 0 to 1. Secant squared dx is the same as du. In tangent x to u, you have e to the 100 u du. Now the antiderivative of e to the 100 u is 1 over 100 e to the 100 u, where you plug in for u equal to 0 and 1. So it is 1 over 100 e to the 100 minus 1 over 100 times 1, or 1 over 100 e to the 100 minus 1. Clearly, this is an integral no calculator can do, because the number e to the 100, I think, is too complicated for most calculators. If you have a very fancy calculator, they might be able to handle it. This a regular calculator, I think, cannot. Okay. If you hear something in the background, that is my son drumming. Don't want to stop him. He seems to really enjoy playing the drums at the moment, so I hope you don't mind. Okay, e to the x integral a to the x dx And the other main formula you need on your formula sheet, that a to the b is the same as e to the b times the logarithm of a. So if you use this formula here, then this nothing becomes nothing but the integral of e to the x times the logarithm of a dx. Where the logarithm of a is some constant, x is the variable. And now you use the basic formula for antiderivatives of e to the x. So it's 1 over the logarithm of a of e to the x times the logarithm of a plus a constant. Now you use the formula again, then it's 1 over the logarithm of a to the x plus a constant. Maybe in this another formula you use, which is useful if you have, no, it's not useful, that comes in chapter 7. But this is not very useful, I guess, because you do not know yet how to take the derivative of the antiderivative of the logarithm. Okay, so these were my first problems, and I think now we have 2 or 3 more, then we are done with integration and we go to volumes. And by the way, all the integrals I covered, these are all, this type of integrals will be in the final exam. So I consider them to be basic integrals. And if you look at the homework problems in chapters 5, you will see many of these problems are there. So is the next problem now the integral from 0 to 3 of x squared minus 4 dx. And whenever you see an absolute value sign in integral, that's a rule, whenever there's an absolute value sign, you have to figure out where is the function that is inside the absolute value sign, positive or negative. So you have x squared minus 4. If you turn on your graphing calculator, this has 0 and 2 and minus 2. So it's a parabola that looks like this. Here it's at 0, it's at minus 4. And you go from 0 to 3. And then at 3, you are at 9 here. No, 9 minus 4, you are at 5. Yeah? And now you take the absolute value of this. So you look at this area and you look at this area between 0 and 3. Where if you take the absolute value sign flips it all. So then the area at the end becomes this area here and this area here. So x squared minus 4 is the parabola. The absolute value makes the negative pieces of the parabola positive. And now you have to compute this area. So that is then the same as the integral from 0 to 2. So this is now this integral here. And there you have to flip around the function. So you really don't look at x squared minus 4. There x squared minus 4 is positive. So the absolute value flips the sign. So this becomes 4 minus x squared dx. In between 2 and 3, x squared minus 4 is positive. Now you have the integral from 2 to 3 of x squared minus 4 dx. And now I leave it to you. Now you can turn on your calculator and you figure out what this integral is, or you just do the antiderivatives. So it's 4x minus x to the 3 over 3, where you plug in 0 and 2, plus x to the 3 over 3 minus 4x, where you plug in 2 and 3. And then you get what the result is. Again, absolute value sign will be in the final. That's an important problem to understand. Now finally, the last problem. The integral of x times e to the minus x squared dx. I do not think there is any algebra possible you could possibly do. So the only possible way to proceed is to make a u substitution. I see u equal to x squared, then the derivative is 2x. I see the 2x up to a constant, there's the x. So if I take u equal to x squared, or you could take u equal to minus x squared, whatever you want, then du dx is 2x, or x dx is equal to 1/2 du. So if I take this as the u substitution, then I get the limit if n goes to infinity. If x goes from 0 to n, then u goes from 0 to n squared. X dx is 1/2 du, and e to the minus x squared is e to the minus u du. Now the antiderivative of 1/2 e to the minus u du is minus 1/2 e to the minus u, because the derivative of minus 1/2 e to the minus u is 1/2 e to the minus u, where you plug in 0 in n squared. If I plug in n squared, you get minus 1/2 e to the minus n squared. And if you plug in 0, you get minus 1/2. So, and if you take n going to infinity, e to the minus n squared will go to 0. So this whole thing becomes then 1/2 minus 1/2 is 1/2. Okay. So these were the integral problems.
ERMHS.
I'm so sorry. Okay, now let's go to some volume problems. And in the volume problems, I have to first turn on my screen again, because first I have to work with my hands now. Let me turn on my video. Okay, now what we are doing is we are rotating vertical slices or horizontal slices around a certain axis. And some of you might have problems visualizing what it means to rotate a vertical or horizontal slice around a certain axis. So for this, you have to look now at this pencil. So that is my slice. That would be a horizontal slice, and like this, it's a vertical slice. Then my hand, like this, it would be a vertical axis you rotate it around, and like this, it would be a horizontal axis. Okay, now in the problems, this would be a vertical slice rotated around a horizontal axis. And if you cannot visualize it, do it mechanically. So you rotate the slice around the axis, and then your eyes have to follow the shadow. So if you follow the path of this slice, you will see you have generated a washer. Again, next situation. Now I take a horizontal slice and I take a horizontal axis. If I rotate this horizontal slice around this horizontal axis, this will generate a cylindrical shell. Next situation. I have a vertical axis of rotation and a horizontal slice. Now, if I rotate the blue slice around the axis, this will generate a washer. Whereas if I rotate a vertical slice around a vertical axis, this generates a cylindrical shell. So if you have questions about this, please ask now. I do not think this is something to memorize. You really have to visualize it. And if you cannot visualize it, then you do it mechanically. A vertical slice, a vertical axis, you rotate it around it, and this will create a cylindrical shell. A vertical slice and the horizontal axis, you rotate this around it, this will generate a washer. So that is the main thing about volumes. You have to know it's either the washers or the shells, and you have to know the base formulas for each of these. Okay, now let's do a problem here, where I have now switched again between share screen and what we are doing. So let me go back to my notebook here first. And let's take as an example the following region. And first we compute the area of this region by using vertical slices. So here is a slice of this region. Now, if I do vertical, slices and I look now at the area of the blue slice, this is length times width. So it is the height, which is square root of x, that's the length of the rectangle. The width is dx. And I do this for all x between 0 and 4, and I sum it all up. So this will be the area of this region. Now I take a horizontal slice. So that means I fix here a y. And whenever I do horizontal, everything has to be in terms of y. So if y is equal to x, then x is equal to y squared. So if I fix here a y and I want to compute the x that belongs to it, then this x is equal to y squared. So if here is y, then here is y squared. Okay, now again, let's set up the area with horizontal slices. What is the area of this rectangle? It's the length. The length is from here to there, so it's right minus the left. So it's 4 minus y squared. The width is a small increment in y direction, it's dy. And you do this for all y's between 0 and 2, and you sum it up. Okay, now comes the moment of truth. Now you turn on your calculator, even if the problem doesn't ask you to do it. Plug this in, let your calculator compute that definite integral, and let your calculator compute this definite integral, and if the two numbers are the same, you know you did it right. And if the numbers are different, then you know you made at least one mistake. Okay, so this was the easier part. This was doing the areas. Now we do the same problem again. Now we take this region and rotate it around an axis. Why is this not working again? Sorry, I have to stop sharing. Let me try it again. So this is our region. The curve is y equal to square root of x. That's what you use when you do vertical slices, and when you do horizontal slices, you always have to solve for x. Then x is equal to y squared. Okay, now let's put an axis, and for the fun of it, I take now, this is my rotation axis here. So I rotate everything along the line y equal to minus 1. Here's minus 1. So I rotate everything, this whole region, about the line y equal to minus 1. And I want to compute the volume of the solid generated by rotating this around the axis. So first, let me take again a vertical slice. So in this case, my axis is a horizontal axis, and I take a vertical slice. If I rotate a vertical slice around this axis, this will generate a washer. So the base formula, what we are using here, if I compute now the volume, I have to use the approach with washers. And the washer formula is pi times the big radius squared minus pi times the small radius squared, and you multiply this with the thickness of the washer. Okay, we have to go back into the picture. You hold your arm out and you have a pencil and you ask yourself, what is the big radius and what is the small radius? So in this case, the big radius is from here to there, and the small radius is from here to there. And to believe it again, you should do it mechanically, have a pencil, put your arm out, rotate around it, and then you see, ask yourself, what is the big radius and what is the small radius? And you will agree with me, this is a reasonable way to do it. So going back to the formula, so what is the big radius? So the big radius, we fixed an x. Then from here to there, this is the height, this is the square root of x. And then you have to add, so this is this piece from here to there, that's the square root of x. And from here to here, it's 1. So it's the square root of x plus 1 squared. Big radius, if we fix an x from here to there, this is the square root of x, and from here to here, it's 1. And you subtract from this, the small radius is 1. And you multiply this with dx, that is the thickness, and you do this for all x between 0 and 4, and that will give you the area of the washer. In this case, the area of the solid, yeah, if you add up all the areas of these washers. Okay, and now we do the same thing again, but we do not take vertical slices, now we take a horizontal slice. Horizontal means everything is in y. So if we fix here a y between 0 and 2, and if this is the y, then the x value that belongs to this y is y squared. Again, if you hold out your arm, if you hold out a pencil and rotate a pencil around the green axis around your arm, you will see that this red slice generates now a cylindrical shell. And for a shell, the base formula of a volume is 2 pi the radius times the height times the thickness. Now you have to go back to your picture and identify what is the height of the shell, what is the radius of the cylindrical shell, and what is the thickness. Now in this picture here now, the radius, when you rotate the red slice around the green axis, the radius is from here to there. So that is the radius. The height is from here to there. And the thickness is a small increment in y direction. So in my case, it is 2 pi. The radius, from here to here, it's y. From here to here, it's 1. So it's y plus 1. The height is the right, which is 4 minus the left. It's y squared. And the thickness is dy. Again, from here to there, it is 4. And from here to there, it's y squared. So the length, the height of the thing is 4 minus y squared. And I do this all for all y's between 0 and 2. And that gives me now the volume if I do it with the shell method. And again, the moment of truth comes now when you plug this into your calculator, you get out a number. You plug this into your calculator, you get the numbers. And if the two numbers are the same, you know you did it right. And if they are different, at least one of your integrals is wrong. Okay, that was all I wanted to do today. If you have any questions, please ask now, and then I try to do more of these questions. If there are no questions, please send me an email should you come up with more questions. So maybe we can have another practice class tomorrow. If there is something you want me to do, please send me an email, then I will announce the practice class tomorrow. Otherwise, I see you all on Friday morning at 10 o'clock.
Dr. Nobrender, how long do we have to take the final?
So the final is, it's a 90-minute final, and I give everyone at least double time. So the final is for 90 minutes. I expect to be there for 3 hours.
Okay.
And also for you, it's important. So it would be, I think it's some of you might have a final at 12:30. Yeah?
Mm-hmm. Oh, I don't.
So if you have time, that is good. If you have a final that starts at 12:30, then it might be a good idea that you take the makeup final on Saturday. Which, again, I have to say, will now be an entirely different final, just out of fairness. Huh? So there are people who have conflict. For them, I offer a final on Saturday, but this is not a makeup in the traditional sense that it's the same final. This will then be really a different final. Are there other questions? Okay, then if there is something, stay either on the line, talk to me later, or send me a brief email. And if there's nothing, I wish you good luck on Friday. Then I hope you contact me if you are worried about your final grade. Thank you all.
Thank you.